You might have all heard that a computer works on zeros and ones. But where are these zeros and ones? I'm sure you write a lot of programming languages, but you are never actually dealing with these zeros and ones. This 0 and a 1, these are the smallest form of memory that you can occupy in a computer. That means this 0 and a 1 is called as a bit. And I'm sure you might have heard about 32-bit processor, 64-bit processor. What does that mean? It means how many bits your processor can handle in parallel. A 32-bit processor can look at 32 bits and a 64-bit processor is double the size. So you can naturally assume that it is gonna process more tasks in parallel. So why is all of this important? You might have already guessed. Because if you're working at the bit level, then you don't have to worry about the high level language and you can perform all of the operations very, very fast. Hello friends, welcome back to my channel. In this particular series, what I want to focus is the fundamentals of bits. Like what are bits? What are some of the logical operations? And how can you manipulate these bits to perform some basic calculations? For example, swapping two numbers, dividing a number by 2, incrementing a number. How do you do all of that? We are gonna take up all of these bite-sized topics and cover most of the fundamental operations that you might be interested when it comes to bit manipulations. And by the end of the series, you will surely understand why do some of these tech companies really like you to know about them. Because they make your program very, very fast. So without further ado, let's get started. To set up a solid foundation, you must first understand the very basics. What is a bit and how does it come into existence? As I already told, a bit is the smallest form of memory available. So when you're talking about the smallest form of memory, it can only have two states. Either it can be set or it cannot be set. Thinking about in electronics, either the current will be on or the current will be off. There cannot exist any other state. And we just build on top of it. So when I'm saying 0, it means that the bit is not set. And when I say that the value is 1, it means that the bit is set. This is the most fundamental and the most basic calculation that you can ever have in a computer program. So you might have also known that 1 byte is equal to 8 bits. So what you can think is, you can think about your computer memory something like this. And all of these 8 bits make up a 1 byte. So in this 1 byte, you can have any number available. You can write something like this. So what is happening over here? This bit is set, this is not set, this is not set, this is not set, this is set, and so on. You get the idea. The interesting part over here is the amount of data all of these 8 bits can represent. You know that these are binary numbers and these binary numbers can make up decimal numbers. You represent 1 byte like this. You take thousands of these bytes and then you get 1 kilobyte, and then you take 1000 of these kilobytes and then you get a 1 gigabyte. That is how the memory expands, and you can imagine the amount of data you're storing. And this is all the way your memory works. Before moving further, let us do a quick revision on what do these binary numbers actually represent. How do you convert these binary numbers to their decimal forms? For example, I have these two numbers available over here. Now you want to see the decimal equivalent of them. To do that, the steps are actually very, very simple. You start with the rightmost position. This is 0, then 1, then 2, then 3, and then a 4. To convert it to decimal, what do you do is, first of all, you write down 2 to the power of 0, then you write down 2 to the power 1, then you write down 2 to the power 2, and then finally 2 to the power 4. Basically, I have written all of these indices and I have given them power of 2. Now, the next step is you take each of these numbers and then you multiply them with all of these. Starting from the very right, I get 1 into 2 to the power 0. Then I have 1 again. So I say 1 into 2 to the power 1. Then I have 0. So I'm going to write down 0 into 2 to the power 2 and 0 over here. And then in the last, I have 1 again. So I say 1 into 2 to the power 4. When I calculate it, I get 16 plus 0 plus 0 plus 2 plus 1. When I add up all of this, I get 19. It means this particular binary number is representing 19. In other words, I can also say that to represent the number 19 on my memory, what I will do is I will take up the block of 8 bits, and amongst those 8 bits, I am gonna set the 0th bit, then the first bit, and then the 4th bit. This memory block now represents the number 19. And that is how all of the calculations happen in your memory. Similarly, let us take up a bigger number. Once again, we have to follow the same approach. I say 0, 1, 2, 3, 4, and then a 5. And now I will write down 2 to the power of all of these indexes. The next step is to multiply each of these numbers with these numbers. Once I calculate it, I get 32 plus 0 plus of 8 plus of 4 plus of 0 and plus 1. So what I am saying is, to represent 45, this is how I need to set bits on my memory. And this is the fundamental concept, how you are storing everything on your memory. You are just using zeros and ones to store all of the data that you need. This is how you go from binary to decimal. But what about the other way around? Let us say I'm given this particular number, and now I have to find out the binary equivalent of it. Well, the method is very, very simple. What you do is you take this number and then you divide it by 2. You get 98 with a remainder of 1. Now continue this process. What do you get? 49 over here with a remainder of 0. 24 with a remainder of 1. Then you get a 12 with a remainder of 0. Then you get a 6 with a remainder of 0. Then a 3 with a remainder of 0. And then you get a 1 with a remainder of 1. Notice that as soon as you get a 1 or a 0, that is where you have to stop. And now, to get the binary representation, what you're going to do is you're going to start looking at all of these remainders that you are getting and start to put all of these numbers in the same order in your memory. So I had a 1 over here. This comes at the first position. Then I have a 0. So this comes over here. Then I have a 1 again. Then I have 3 zeros. And then I have a 1 and a 1. It means to represent the number 197 in binary, this is how you're going to represent it. Similarly, we can take up one more example for the number 45. So I start with 45 and then I divide it by 2. I get a remainder of 1. Then I get 11 with a remainder of 0. Then I get 5 with a remainder of 1. Then I get 2 with a remainder of 1. And then I get 1 with a remainder of 0. To get the binary equivalent, you start from the very top and then start filling all of these numbers one by one. So basically, I am saying that to represent 45 in binary, this is how I need to set all of my bits. This kind of solidifies our basic concepts. You have now understood how to take up a binary number and represent into decimal. And similarly, how do you take up the decimal number and convert it to binary? But this is just the beginning. You have now set up everything in your memory. But the main importance is how you can operate upon them. Because just storing things in memory doesn't give you anything. You want to perform operations on it. You want to change them. You want to perform additions and subtractions. How do you do all of that? Well, all of these things come after a certain time. You first need to understand the very basic operations that you can start to do upon two numbers. And we are talking about binary numbers over here. So if you have a 0 and a 1, what sort of operations are possible on it? The first three operations that we will be looking at are AND, OR, and NOT. Now, if you think about bits, you only have two values possible, either a 0 or a 1. So, if you have to perform operations between them, you can see that you cannot have any more operations possible. You have all of the four combinations available. If you try to make any other combination, it will be a repetition of all of them. It means this list is exhaustive. You're gonna cover all of the different possible operations. Similarly for OR, you are comparing two bits and these are the only possible operations upon them. NOT is a little bit different. It is a unary operator. For example, binary operators are which work on two numbers, either 1 or a 0. Very similar to how you have A plus B. You need two things. But an operator like factorial, you can have 5 factorial. It just needs one operator, right? Similarly, NOT only needs one thing. So when you have two options available, 0 or a 1, that is how we are putting up the NOT operator. Now let us try to understand all of these values. When you say 0 and means inclusive, you have to cover both the things. So when it comes to 0 and 0, the result is always 0. And operation simply means that if you have a 0 anywhere, then the entire thing will become 0. It will only be 1 when all of the operations are 1. You can think of it like an electrical circuit. You can think of 0 and 1s just like electrical switches. So if you have a wire and 0 and 1s are the switches on them. So if and only if all of the switches are on, then only your current will be flowing. If any of the switch is off, then your current will not flow. And this is exactly how the AND operation works. So think about this. If you have both the switches as off, then no electricity will flow and the result is 0. Think about the next scenario, 0 and 1. One of the switches is off and other switch is on. So the current will still not flow and the result is 0. One switch is on and the other is off. So once again, no current will flow. 1 and 1. It means both the switches are on. Both the bits are set. It means the answer will be 1 over here. When it comes to AND, it simply means that when all of your bits are set, only then the answer will be 1. In every other case, the answer will become 0. Similarly, now try to take a look at the OR operator. Think about OR operator like either. It means that in an electrical circuit, if you have any of the switches as open, or I am saying that if I have any of the switches on, then I will say that, okay, the current will flow. You can just think of it like, okay, in this entire circuit, do I even have a single switch that is set to on? If yes, the answer will be 1. So when I'm looking at OR, 0 or 0, it means none of the switches are working. So what will be the answer? The answer will be 0. In the second scenario, 0 or 1, one of the switches off and one switch is on. Try to think like, okay, in my entire circuit, is there even one switch that is open? If yes, the answer will be 1. 1 or 0, it is the same scenario. So I say 1. 1 or 1, I still have any one switch open. So I'm going to write down 1 over here. This is how you perform the basic AND and OR operations. What about the NOT operator now? This is fairly very simple. NOT operation simply means negate whatever you currently have. So if I have a 0, NOT of 0 becomes 1 and NOT of 1 becomes 0. It simply means that I'm reversing the switch. If it was on, I set it to off. If it was off, I set it to on. You can see that all of these operators are fairly simple to understand. But the magic happens when you start combining all of them. You combine some of them in an AND block, you combine some of them in an OR block, and then you have a bigger circuit available that is combining all of these things. That is where the magic actually happens. And while we're discussing all of these logical operators, there is one operator that behaves very differently. And that is known as the XOR operator. It is a short form for exclusive OR. Now, it may seem that it works just like the OR operator, but it is a little different. The idea over here is, and that is how I like to understand, and it has always helped me. For example, if I'm given a lot of binary numbers, a lot of bits set like this, either 1 or a 0 or anything, then the answer will be 1 when there are odd number of 1s. You can see that I have 3 1s available, so the answer will be 1. It is a very simple calculation. If you are given an entire expression, if you have odd number of 1s, then the answer is 1, otherwise the answer is 0. For example, if I look at this particular expression, I have 4 numbers available, right? But I only have 3 1s available. So the answer to this particular expression will also be 1. In any scenario, if I had one more 1 available over here, then this would have changed to 0 because now I have 4 1s available. And this is how the exclusive OR operator works. And it is very interesting. So now, if we try to apply the same exhaustive list using the XOR operator, how will our results look like? I have 1 XOR 1. How many 1s do I have? I have 2 1s. That is even. So the answer will be 0 over here. In the next 2 scenarios, I have 1 XOR 0. That means I have 1 1 and that is odd. So answer is 1. 0 XOR 1. This will be again 1. And look at the next case, 0 XOR 0. How many ones do I have? I have 0 ones. That means it is not odd. If not odd, I'm simply write down 0 over here. So this is how the exclusive OR or the XOR operator works. At this point, we have now established some of the very basic logical operators. Try to think about this like mathematics. What are the first things that you learn? You learn about numbers and then you learn about addition and subtraction. It is the very similar concept. You learned about bits and now you learned about the basic operations that you perform on them, AND, OR, XOR. But similar to mathematics, now you were adding bigger numbers instead of just single numbers. For example, you first added 2 plus 5, but now you are adding multiple numbers. For example, 356 plus 512. That is advanced, right? Similarly, you also perform these advanced logical operations in bitwise also. For example, I'm gonna look at AND, OR, and XOR for two particular binary numbers. I have these same binary numbers and I am gonna perform the AND, OR, and the XOR operation. And how do you do it? If you are given these two numbers, you do not take a complete AND. It is not even possible. How does it work? All of these numbers, they are represented as single bits, remember? And when you are doing a AND of two memory blocks, it happens in the following way. You will do a AND of both of these numbers and write down the result here. Then you will do a AND of these numbers and write down the result here. And this is how you will go on. So if I have to write down the AND, 1 and 1, that will be 1. 0 and 1, that will be 0. 1 and 0, it will be a 0 again. 1 and 0, it will be a 0 again. 0 and 1, 0 again. 1 and empty. When it says empty, you can assume a 0 to be over here. So 1 and 0, and that gives me a 0 again. So basically, if I do a AND operation on these two binary numbers, all I get is just a 1, and that is it. And this is how you perform a logical operation on bits. Similarly, let us try to do the OR operation. And once again, we will follow the same approach. Just do a OR on these two numbers and write down the result. So 1 or 1 is 1, 0 or 1 is 1, 1 or 0 is 1, 1 or 0 is 1, 0 or 1 is 1 again, and 1 or 0 is 1 again. So the OR operation yields you this particular result. Let us now try to look at the exclusive OR operation. The approach will be again the same. I will take up these two numbers and write down the result. So 1 XOR 1, that will be 0 because I have even number of ones. 0 XOR 1 is 1, 1 XOR 0 is 1, 1 XOR 0 is 1 again, 0 XOR 1 is 1, and 1 XOR 0 is 1 again. Therefore, if I perform these logical operations on these two binary numbers, these are the following results that I'm gonna get. And this is basic mathematics for you when it comes to binary numbers. I would like to talk about exclusive OR a little bit more. It is actually very, very special. If you think about it, we established three fundamental expressions. 1 XOR 1 is 0, 1 XOR 0 is 1, and 0 XOR 0 is 0. What I'm trying to say is that I have 1 XOR 1. Basically, what I'm trying to say is that if I take up any number and then I XOR it with itself, the answer will be 0. If you think about it, how does it work? Let us say the number was 1101. And now I am XORing it with 1101. If you remember, how were our logical operations working? I had 1101 here and then 1101 here. Now I am XORing the number with itself. So this will happen at every level, right? At every column. And for every column, 1 XOR 1, that is also 0, and 0 XOR 0, that is also 0. So when I XOR these two numbers, all of them will become 0. And this is true for any number that you have. And this is a very generic statement and it is used in a lot of programs. This will help you to actually speed up your program. So this is one fundamental rule that you always need to remember. The other rule that you need to understand is this particular number. You are saying 1 XOR of 0 is equal to 1. Basically, I am saying that if I take up any number and then I XOR it with 0, then the result will always be the number itself. And once again, you can try to verify it. For example, I had the number 1101 and I am XORing it with 0. So basically what I'm saying, 1101 and then I XOR it with 0. So what is happening over here? Now, if I take up each of these columns, what I'm doing, for every column, I am XORing it with 0. And when I do 1 XOR 0, I get a 1. If I do a 0 XOR 0, I get a 0. Then I do 1 XOR 0, that is 1 again. And then 1 XOR 0, that is 1 again. So in the end, what did I get? I got my same number back. So these two properties of XOR are very, very important. Any number when XORed with itself will give you a 0, and any number when XORed with 0 will give you the number itself. So try to think like this. If you are given an array in which every number is duplicated and only one number is unique. For example, you are given 2, 2, 3, 3 and then a 4. What happens if you XOR all of them? All the duplicate numbers, they will turn out to be 0. So 2 XOR 2 comes 0, 3 XOR 3 comes 0, and then you have a 4 remaining. So 4 XOR of 0 again, what will that give you? It will give you the number 4 itself. So is it safe to say that if I'm given such an array and I XOR all of the numbers, whatever is the result that I'm remaining with will give me the unique number in the array. Let us look at it again. Example, I had the array like this. Now you can see that 2 is duplicated, 3 is duplicated and 4 is duplicated. Only 5 is unique. So if I XOR all of the numbers, I get this and I can also arrange it in this way. What does that give you? 2 XOR 2 becomes 0, 3 XOR 3 becomes 0, 4 XOR 4 becomes 0. When you do 0 XOR 0 XOR 0, once again you will get a 0. So all of this can just translate to 0 XOR 5. And any number XOR of 0, the result is the number itself. So I will get a 5. So what are we doing? We just XORed all of the numbers and then I am getting whatever was the unique number in the array. And that is why all of these bitwise operations are very, very helpful. If you understand these fundamentals, you will be able to take advantage of them. Otherwise, you might be looking into some complex techniques like iterating the array and doing some sort of things. I would like to stop over here for this particular video and take a moment to digest all of this information. Try to understand how all of these bits work. How do you set a bit and how do you unset a bit? How are these operations working? Just try to take any random binary numbers and perform all of these operations. I would like you to emphasize on the exclusive XOR operator also, because that is very, very handy. And in the comment section, I would like to know what sort of problems do you see when it comes to the exclusive OR operator? How have you taken an advantage of it? Because if you can get that kind of a compilation, you will immediately understand that, okay, using the XOR operator will give me a very fast solution. In my upcoming video, we are gonna actually start on the bitwise operators. That means how can you actually play with the bits itself? How can you shift the bits in the left direction or the right direction to get even more results? So stay tuned for that video. And if you haven't yet subscribed, subscribe now so you get notified and don't miss that. Along with this, I would also like to give a huge shout out to all of the channel members who support my channel. You guys really keep me going. And as a member, you do get try to reply to your comments and early access to new videos as well. And also remember, now you can schedule a one-to-one session with me and we can discuss about almost anything. Stay tuned for my upcoming video. Until then, see ya.